So, good day. I am back. I skipped last week for family matters, but there has been a lot of progress in Argyll over those 2 weeks, so I'd like to talk about them. But first, I want to diverge a little bit. I want to talk about Claude Code, which is how this kind of all started. I would not have started this project if it weren't for Claude Code, and just remind people that if you were to solely rely on vibe coding and leave it to product managers or people who are not engineers to drive these tools, the mileage may vary and it might vary a lot. And so, what I'm going to show now is actually some code, which I don't often do. So, the way that I originally wrote the system was that I did it in a very declarative style. So kind of big specs where I described the properties of the system and how it should behave as I was working in it, and usually in big swaths. Like you can call them one shots, but they were more of like, here's a massive spec. I want you to generate a plan, and then we'll work the plan step by step. But that was generally the approach. Now that has changed. Since then, I actually treat Claude and Codex more like a pair programmer, sort of like a sidecar sitting there and bouncing ideas off of, and so on. And part of the reason why it's changed is because of the performance story that I've talked about on this channel in the past weeks. Is that in the very first iteration that Claude produced for me, even though I thought I was pretty clear about the properties of the system and how it should behave, Claude was very satisfied with 250 flows per second, mind you, against a Redis backend, and Redis is memory bound, right? It's not heavily I/O bound. It thought that that was totally fine, and it even gaslighted me into trying to believe, to make me believe that it was totally fine, which it isn't. And throughout the project, one of the things that I did is that I would, as I reviewed the code, and I'll be honest here, because of those big bangs at the beginning, I didn't review the code as well as I should have. Now these days, I review it really, really well because I do small, focused, incremental changes to the code base over time, much the way that a normal engineer does, but I'm just using AI to accelerate that and like keep the work in progress low, keep things focused and sort of goal driven, right? Which is good because that's the name of the project. And I missed a lot. I missed a lot because of those big bangs and because of the just sort of mass proliferation of code into the code base based on just trusting blindly that Claude knew what it was doing. Now, there are dozens of examples, and some have had major impact on the performance. But here's one that is seemingly innocuous, and I just want to go over today because I think it's a good way to highlight some of the downside of using these tools blindly and not bringing an engineer's hat to the table when you're actually building the tools themselves. So I may have talked about it. One of the modules that I wrote to support Argyll is called timebox, and what timebox is a event sourcing. It's a very opinionated event sourcing system. The opinion is that the aggregates should be as small as possible, and that it shouldn't accumulate a lot of events. Although over time, I've found that the only way for the system to work properly is for some aggregates to just continuously aggregate events. Totally fine. I was able to work around that. But some of the core things, the core entities in this system, of course, would be an event, right? An event is basically your currency for event sourcing. And so this is what event looks like in timebox. It is an envelope, right? So the actual event payload is the idea originally was that we store the event payload in JSON, and the reason why it's in JSON is that we don't have to reason about how to marshal it in and out from some obscure format like protobuf or something like that. That may change in the future. I think for now it's okay. And because we were using Redis, it made it really easy to debug. So like I could just look at the event and know exactly what was being persisted. But you can't live on JSON raw messages alone. You actually need to convert those payloads into real Go values at some point, and usually you're actually converting them from Go values. And so Event also has a way to memoize or just hold on to the original value that it used to create that JSON payload. Specifically, the way that it's done is with a Go any, and if you're familiar with Go, an any is basically an empty interface. It's an alias for empty interface. And the property of an empty interface is that because it doesn't define any methods, it will accept anything. And so that's how we're actually storing the original payload Go structure or value. It could even be a string. It doesn't have to be a struct. In order to do that, of course, we need a mutex because it is concurrent code. It could be that multiple people are trying to actually do this memoization or retrieval at the same time. And so I'm using a read-write mutex. The property of a read-write mutex is that you could have many readers, but as soon as a writer comes in, the writer has to wait for all the readers to release the lock, and then the writer gets it. And so in the meantime, nobody can read the mutex. That's the idea. Now, generally speaking, I don't use a lot of mutexes in my code. I will rely on some of the higher level abstractions like channels and Go routines to do things. But in this case, it's actually necessary. And so that is the structure itself. Now, how do I get the value out of the event? Because as you can see here, it's not exported, right? So it's not an available field for just a normal API consumer of an event. You actually have to use a function or a method to retrieve it. And also that function or method has to do the work of saying, hey, I don't actually have a memoized value. I actually need to use the JSON to convert it back into a Go structure or Go value. So the original code for that was here. It's called get value. And I don't know if you can see that. Let me see if I can make it a little bit bigger. It was a method on event itself, and it was private because it was being used internally by other functions that were public, right? So like appliers and handlers and stuff like that, because they needed to be able to get the value and basically perform callbacks. Now, one of the things, if you're a Go programmer, you might notice about this code right away is that when I call get value, I'm providing to it a target. And what a target is it means that the caller itself has already allocated a target object for it of the type that it's trying to coerce it into on the way out of the function. But important is to read the comment on the function, because again, I was very spec-based. I told it the properties that it should exhibit. And so I'm going to just read it out. Get value unmarshals the event data into the specified type. Here the specified type is whatever the type of target is, because it's an any. It uses a cache, that's the dot value, to avoid repeated unmarshalling from raw JSON bytes. This is safe for concurrent access and intended for use by make applier. That was true. It still is true. The documentation is actually correct. It does document what I intended for this function to do or this method to do. But then when you get into the implementation, you start asking questions. So here, let's walk through it real quick. We have our read lock, right? So the first thing we want to do is check, is there already a memoized or cached value? If there is, meaning it's not nil, what we can do is we can immediately release the read lock because we've got a value that we can work with. And the idea here is that once that value is set, it's never changed. It's basically just it's immutable because we assume that everything is pretty much deterministic. And that it would be an edge case if you wanted to target a different type. Normally that type will always be sort of a one-to-one between what's actually memoized, so it's fine. So what do? Okay, we release the lock and then we JSON marshal it? Why? Why are we taking the memoized value and converting it to JSON? That doesn't make any sense, especially since the comment itself said that we want to avoid repeated unmarshalling from the raw JSON bytes. I don't know, but this is what Claude decided to do. So we try to marshal it. If there's an error, we return the error. Obviously, it's Go, so you're going to see a million of those. And then after that, if it was successful, we immediately turn around and unmarshal it back into the target. Okay, now this is how things in Go were often done before generics. Um, Also, most of the time, what you would end up seeing in Go code is that you would just call JSON on Marshall directly in line with the code. You wouldn't create sort of a generic method like this anyway. And mainly the reason for that was probably because of situations like this. Let me go a little further in the code because there are some Go-isms here that stay, they remained. If it wasn't memoized, we want to release the lock, the read lock. And then we will immediately attempt to get a write lock on it. And the reason why is because now we're going to do some dirty work to actually store the memoized value. We will defer the unlock, which is pretty common Go pattern. And then we will then again check. Again, we will check if the value has been memoized. Why? Because there could have been a race condition, and in the meantime, the value may have actually been memoized before the write lock was actually acquired. This is pretty common in Go as well. But once again, we see this pattern. And the question is, why do we see this pattern? I asked Claude, and like all AI tools, if you point out their folly, they're like, oh yeah, you're right, it's totally wrong. Yes, and I shouldn't have done it like this. That's it. That was the best answer I could get from Claude. It'll then go and it'll do the real work, right? The idea here is that we want to unmarshal it, and then marshal it again into the target. It's just bizarre code. I almost don't even understand it. So let me show you the code that any normal Go programmer would actually have written. This is how it works now. Here's a get event value, and it's now a function rather than a method, and the reason why is because I'm using Go generics. The contract hasn't changed, it's still the same. And the reason that I'm using Go generics is because that gives you a little bit more power in being able to actually do a type check rather than a targeted JSON on Marshall, which doesn't make sense. So here's the code. I acquired the read lock, which we still need to do. And of course, we passed in the event. It's not part of the receiver anymore. So it's now just a normal parameter going in, as well as the type that we're looking to receive. So I acquired the read lock. I then check to see if the memoized value is of the type we're looking for. The important thing there is that because the memoized value is actually an any, if we wanted to do a type check, we don't have to check to see if it's nil. Because if it's nil, it's not going to satisfy the type check anyway, and it will just return false, right? So that's you get that for free, which is good. But if it does match the type, it will release the read lock immediately and then return the value. That's it. That's how you're supposed to do it. Now, if it didn't, it will release the read lock, and then it'll basically change to resolve event value, meaning like it actually has to do the real work. So here we get it again. We acquire the write lock, we get the value, and we of course we're doing a type check again. We have to do that again. That race condition is real and we can't avoid it, right? So it has to be done, but it's much more lightweight this time. And again, if it's okay, then we just return the value immediately. All good. We don't have to do anything. Now, if it's not, then we do all that work that we saw before. With the exception that we're unmarshalling the event into the targeted type that we're looking to target, and then we only have to do it once. Where I don't know what it was doing in the other one. It was batshit, like it was crazy code. I'm glad it's gone, but I guess the point is that you got to review the code that these things are producing, because this code passed the test. And in fact, all of the code that was bad and slow and just really not working in even close to a normal way, and I'm not even talking about optimization here, I'm talking about just normal, they all passed tests, all of the code. And it reminds me of what Rich Hickey said about bugs in production, I think. It's like, what's true about 100% of bugs in production? They all pass the tests. And these are not technically bugs. They do pass the test, but if you consider them non-functional requirements, meaning like my system should perform better than 200 flows per second, then these things accumulate. And they accumulate up to 50 times apparently, because by the time I stopped working on the Redis backend for timebox, the performance improved by about 50 times. So it went from 250 flows per second to 12,000 flows per second. That's a considerable change. It's not a trivial change, and it was mainly the result of me looking at the code that Claude was producing and saying, "What are you doing? Are you crazy? Like what?" And I would use more colorful language than that, because it's AI at the end of the day, and I can do whatever I want. I pay it, and really just working through the way the system should actually behave. Not just the properties of it, but the performance of it is important as well. So yeah, there you have it. That's one example. And since we're in timebox, the big thing that I've worked on over the last 2 weeks is that I reached sort of the plateau on what I think I could do with Redis as a backend. And it was always sort of my goal with timebox to be able to support pluggable backends. So that's exactly what I did. I added 2 backends. They're both experimental, of course. One of them is Postgres, which is par for the course. I guess everybody has to have a Postgres backend. And then the other one is a Raft backend. And the way that I implemented the Raft backend was to use the etcd Go library for doing Raft, and then also the etcd bbolt LMDB implementation. Both of them are kind of designed to work really well together, and they do work really, really well together. Interesting property about bbolt is that it's single writer, which means that everything that it does is sort of optimized around the single writer. And so if you're consuming a write-ahead log from Raft, it's actually a perfect fit. I'll get into that a little bit. The performance is not as good, and it's actually quite off. Probably there's some room to improve it. But what I would say about that is that at 12,000 flows per second with Redis, part of the reason it was able to accomplish that is because the fsync value was like every sec. So once every second, it would flush to disk. So you had that 1 second window where if there was a failure, you would lose data. You wouldn't be fully durable. Now, if you tweak that, which you can, so like with Redis, you could tweak the setting and make it fully durable, meaning like fsync always. It would always flush immediately to disk, and so you'd have 100% durability in what it was doing. But then the performance would drop down to like 2,800 flows per second, which again, it's probably fine for like the vast majority of implementations, but it wasn't my target. My target was like, make this as fast as possible, but still correct. It had to be correct, had to be durable. So Redis itself was not going to meet those requirements unless I invested heavily in sort of Redis specific clustering, which I didn't really want to do. I think the idea was that I was always going to look toward Raft as the consensus system. And so this is what I'm experimenting with over the last couple of weeks, and the results are pretty good. They're not great. What I have found is that with etcd and bbolt as the backend, I can do about, I think, 5,500 flows per second. The other thing that was interesting about it too is it doesn't seem to saturate as quickly with that backend as it did with Redis. So with Redis, at some point you would hit a certain number of concurrent workers, and then the performance would actually just start to drop off precipitously. Whereas with Raft, what ends up happening is you'll hit a certain number of workers, and it doesn't, the throughput doesn't actually start to lower. It just sort of plateaus. It stays where it is. So this is kind of a good behavior that you want to see in the system. You don't want it to hit a certain threshold and then the throughput just starts to drop crazy like that. And that's what was happening with Redis. And there's a good reason for that. Redis is single threaded at the end of the day, so anything is going to be bottlenecked at the command level once you start pummeling it really, really hard. With Raft, the way that it works is it'll slow down, but you're creating like a quorum on every command that you present to it, and so it's going to be limited by that throughput. And apparently, it's about 5,500 flows per second at the moment. Now, again, it could be better. So I want to walk through a little bit of it. I think it's interesting just to look at it. And let me briefly talk about Postgres. So the Postgres backend can do about 2,800 flows per second. I created a schema that was, it might not be the most efficient way to do it, but it's probably good enough. I think that it looks like this, right? This is generated code. I didn't really look at it at all. I just wanted to get it working and exhibit the properties that I was looking for. So let's not look at the time box index here. Here's time box events, right? You want to know the store that it came from. You need to know the aggregate ID, the event sequence, and the payload data itself. That's it, right? And the idea there is that there's a primary key that matches the store to the aggregate ID and to the sequence. And the reason for that is because we still need those version conflict depend semantics. So, if you try to insert a set of events, which is exactly what we will be doing in the code, and there is a key conflict on the aggregate, basically on this primary key, it's going to boot it out. You're not going to be able to commit those events because they conflict with events that are already there under that primary key. That's the behavior that we're looking for. That's what we were doing with Redis. It's also what we're doing with Raft, but with Raft we have to do it manually, which is fine. So the interesting thing is that it does exactly what we want, and actually with not a lot of effort, which is great, but it does also have a plateau. Redis does a lot of work behind the scenes. One thing I intentionally made sure that I didn't do is I did not create foreign keys and cascades between these tables, because again, that would be sort of performance overhead. And since this is sort of a contained system, and the code itself maintains the tables based on the events and the things that are changing, I just do that with code, which most ORMs do these days anyway. So it's not harmful, and it squeezed a little bit of performance, but it plateaued quickly, like I said. I also, for testing purposes, created a memory persistence layer. It's just a hash table. There's nothing special about it, but it makes for faster tests. And the thing that I did that was really important in building these backends was to say that the Redis implementation is the reference implementation. And therefore, any of the tests that you do and any of the code that you build must be compatible with what's already there in the Redis implementation, the semantics of it, and the tests that are there. I haven't gone so far as to create a complete compliance test suite to make sure that every backend has exactly the same properties against the exact same set of tests, but I probably will at some point in the future. Now, again, would Claude have done that for you? No. Claude would not have thought to do that at all. Claude would have just wrote the code and maybe some tests that weren't even necessarily that good. It takes an engineer to care about these details. It does. And one of the things I need to tell you as engineers, if you're watching, is that use the tools. They'll make you faster, right? The great thing is that you can try a bunch of different options at the same time, and it's not a heavy cost on your hands to do that, because you can back them up very quickly and sort of regenerate code. You'll be consuming tokens, of course, but you'll be able to actually experiment much more quickly than if you didn't have the tools. And what ends up happening is if you don't have the tools, experiments feel costly, and you're less likely to back out and try something different that might actually be an improvement. And so these tools can actually improve the resultant outcome of the code that you're producing. You just have to invest the time in actually using them. So I'm not knocking the tools. They're great, but they do screw up, and that's a fact. Okay, we now have several backends. The important backend is the Raft backend. And so the code here is pretty straightforward. One of the things about Raft, and I don't want to go too deeply into how Raft works, but it's a consensus algorithm, and the way that it works is almost like event sourcing to some degree, right? Everything ultimately goes into a write-ahead log. The write-ahead log is what's disseminated across the peers. In Raft, there's only one leader, and then there are other followers and potentially candidates, depending on whether or not you're trying to establish who the leader is via an election. But that log, this log of commands, this is what actually gets disseminated across all the peers. And so that's what actually provides the guarantees and the scalability and durability. It also has the ability to snapshot, which is good. It'll just, depending on how you want to implement it. The way that I implemented it was essentially to say, listen, we've got all these commands. We've got bbolt stuff that's been partially committed, but we do want to take big blobs of these commands and actually snapshot them so that if a new peer comes up and it has no state whatsoever, like no history, it can actually reproduce the history up to the current point relatively quickly and then become part of the cluster itself. So again, the interesting thing would be, I'm not going to go too deeply, but that I've broken up the persistence and the store in timebox. So the store itself is sort of higher level, and what it does is it actually does some of like the coordination and some of like the higher level ergonomic APIs that are good for the user of the library, but probably like, aren't the best fit for the way the backend persistence mechanism should work. Another thing that I did, and I don't know if you can see it, you probably can see it in the commands, is that I actually introduced new codecs. So before, the way that timebox worked is it only serialized event envelopes into JSON, because the assumption at the time was that it was going to go into Redis, and the best way to store stuff in Redis is just as a text blob, because you can do something with them. And also we still do that JSON code decode for Postgres as well, and for memory. Actually, for memory, we don't even do that because of the way that I separate it. The backend gets the raw events, and so the memory persistence system just stores the events. Right? It doesn't do anything with them. It's a hash table, like I said. But for the Raft backend, we're doing a binary code decode. So, let's just briefly go through it. I mean, there are two commands that timebox needs. That's it. There's only two commands. So like a lot of Raft will do several commands that it has to deal with in sort of being able to maintain the overall projected state. In the case of timebox, we don't need anything. We need command type append, which appends events, right? And then we need command type snapshot, which basically says that the consumer has decided that it wants to snapshot an aggregate. Here is that snapshot and sequence, and then any of the other information that's actually necessary for storing that snapshot. And the reason why it's important, for the same reason with Redis, is that you may have a snapshot that's actually stored, and what you want to be able to do is take it and then only the difference of the events that have happened after the snapshot was made in order to send it back to the client so that they can create their own projection of that snapshot. Reason why it has to be done in the client is because the client knows how to project that state. The server is dumb and it doesn't make any assumptions about that, so it just accepts the snapshot that you're storing. But as we go in, what we can see is like I've got just very basic constructors like make append command, right? And so the idea there is we get a proposal ID, which is Raft specific. So you propose to the cluster and to establish a quorum, right? And then there's the request itself, the append request. And the append requests are essentially the parameters that you would have passed into append events in the original timebox library. It takes the aggregate ID. It takes the expected sequence. It takes the status that should be indexed, right? So some of the indexing stuff is here, right? Like the way that this is the higher level store. The higher level store does the work of saying, hey, how do I index this stuff? And then it just pushes it into the append request. So this is like a one payload that goes to the backend, and then the backend will deal with how best to persist that stuff. And then, of course, the labels. So there are the labels that need to be stored as part of the indexable representation of the code. And then the events themselves, again, as is, because we leave it up to the backend to decide how those things should be persisted in its backend. So, binary. We make a command, and we give it some buffer to work with, and then we're just going to append to it. And by the way, a command is just an alias for a byte slice. That's it. It just looks good, right? It's better than saying here's a byte slice. It has to have some semantic meaning, and so when you see it as a command, you know it's a command. It can also have methods, which it does. So what we're going to do immediately is like we're going to encode the binary events. So there is a helper called encode bin events. You give it events, and then it's going to encode those events as a binary stream. That's it. So I mean, if you look at it, again, it's basically helper, and we're using make encode all with a function that it closes over, which is bin event. And this is the bin event codec, so that's just an instance of it. So if I go to bin event, where is it? Yeah, so here, the bin codec, right? Here's how you encode an event, and you're giving it like an empty byte slice, and then you're just appending like int64, which is the timestamp. You're appending to that the sequence number as an int64. You're appending the aggregate ID, which is another helper, because an aggregate is a slice of strings. It needs to handle that sort of separately. You're appending the event type, which is just coerced into a string, because it basically is. And then you're actually appending the bytes themselves, like the data of the events. So, I mean the payload. Sorry, the JSON that's already been created. That's it. That's kind of the idea. And then if you were to go back, you've got all of them being encoded because they're part of a single append. Append can have many events. And then what you want to do is you just want to give the command. So every command starts with the command type, which is just a byte. And there are no versions in it right now. My thoughts are I don't want to have an extra byte to sort of convey the version on every command. And so what I'll do in the future is like if we have any sort of like V2 commands, like command type append V2, it'll just be, 3 as the command instead of what it is right now. So I think right now command, append is 0. We have the snapshot, which is 1. So if we had a V2 append, it would just be 2. It doesn't need we don't need to go crazy with how versions are actually represented at the Raft level. It makes no sense to go crazy with it because it's never going to be an egress data structure. It's always going to be sort of internal to the cluster. So we just keep it simple. One thing that I see here is that since we know the encoded event size, we could probably just properly size this ahead of time. We probably should. So I'll do that later. But again, here's a case, and it's not a major one, right? It's not such a big deal. But here's a case where Claude probably should have done that. It should have known better. Here, it's using a magic number. Like there's not even any reason why it should be using that number. 128. Why? Because maybe. Like that's its rationalization. And so. No, this could definitely be improved, but it wasn't one of those things like the get event value problem. One of the things that I found with the get event value problem was that it improved the throughput by 20%. So we went from like 9,000 per second to 12,000 per second with that one change. And the reason why is because those events, they're the currency of the system, right? They're the things that are moving through it very, very fast. And very, very frequently. And so if you screw that one up, that's basically a choke point. It's almost like the John Carmack inverse square root problem, right? So, with John Carmack, he was computing surface normals, and therefore he had to get the length of a vector. And, the idea was like, take the square root of x squared plus y squared plus z squared. Now, the normal way to do a square root is pretty expensive because it has to be correct. And if you're doing that a couple million times per frame, it's just not going to work. It's just not going to be the right way. And so sometimes you have to just go with good enough. And so he basically did it with 2 cycles instead of like several hundred. And so this is the thing. Sometimes little things that seem innocuous, they could just kill you. And that one killed me. This one won't kill us. This is not so bad. It's going to be memory inefficient, but it's not a deal breaker at the end of the day. So I'll leave it like that for right now. And then what I may do is sort of circle back later and make it just a clean, full append from the beginning. I think that's probably the better way to do it. Okay. I've probably talked about the code enough at this point. What I'm going to do is I'm going to actually go and I'm going to start. We're going to look at a performance test, just so you understand. Like it's not great, right? But it's good enough. Start.sh. Pipe that into dev null because we don't care. And eventually it'll start. It takes a little while for it to boot up. Oh, there we are. We're almost there. the start script basically in the background is creating a Raft cluster. So it has to create them all and make sure that they're properly wired up and talking to each other. And so I think we're there. So what I can do is I'm going to run a load test. And I'm going to do, let's just do 1500 for now. And what you can do here is I'm using K6 to do the load testing. I've got like 1,500 workers in this case, and I'm going to run it for 30 seconds. And for the environment, what I'm going to do is inject the engine URL into the script using a script called findLeader. And what findLeader does is basically just iterates over the endpoints that we know are part of the Raft cluster to know which one the leader is. Because the way that the Raft setup works is that the leader has sort of like the hot path for writes, meaning like if you send a mutating command to the leader, like create new flow, create a step, or whatever, it will immediately do the work of establishing the quorum. It's the one who's allowed to do it. And so, you get sort of faster throughput. Now, the way that I implemented timebox is that actually the follower nodes can accept commands and then they forward them to the leader for it to process them. And the reason that I did that is just for sort of like ease of use and so that there aren't any hiccups when the leader changes, because generally when you set up a system like that, if there is a new leader elected, that information has to actually propagate upward to whatever the reverse proxy is, so it knows how to route to the new leader, and there might be sort of like hiccup time in between. So what this allows for is like temporary period where followers are still receiving commands, like write commands, and still being able to make sure that those commands get processed successfully. That's basically it. The script that I'm going to use today is not the simple full script, it's the start script, so it's just creating new flows and that's it. So let's see how it runs. And I think OBS might not be helping the performance at the moment, but it's good enough. And also the 1,500 workers, I think is half of what I was able to get up to before it started to saturate. Although maybe not quite as much. I think it was maybe 2,500, and that's when the sort of like the not the saturation point, but like the plateau point on the performance started to hit. Yeah, so we didn't get as many as we wanted. So we got, in this case, 2,600, probably because of OBS and whatever I have else going on in the background. But it ain't bad. And so now what I'm going to end up doing is I'm gonna quit this. I'm going to start up Docker, just so you can kind of see. We don't need to build. So you can see that actually everything just works the same as it always did. Oh, there's that test step. So now it's gone. Yeah, there's and it's the interesting thing is that if you look at the way that Argyll works and replacing the backend from Redis to the Raft backend, there's very little code that actually changed in Argyll itself. The only thing that had to change really was like the bootstrapping, meaning setting up the Raft cluster so that Argyll knew that was its timebox store. But otherwise, all of the aggregation stuff, it's just done exactly the same way. There was one slight change in how events are published, because the original assumption under Redis was like, if you created a command that went to the Redis backend, you had these sort of onSuccess hooks, and we were using onSuccess hooks to actually create the publisher for the WebSockets. The problem with that is if you were running multi-node, you would only be able to see the things that happened on the node that you were connected to. And in the situation with Raft, that's kind of unacceptable, because if you're round robining, you don't even know. You have no idea which node you're connected to, right? It could be any one of several replicas. And so I did have to create kind of a publisher hook in the timebox Raft library so that we would get event publication for the purposes of satisfying the WebSocket interface. But it's actually a better it's better behavior now, because you can see events that are happening on any node from any consumer, which is great. So yeah, if I start this, as you can see, it does what it's always been doing. Can run in multiple at the same time. I will run just an order creator, right? Maybe payment processor. There we go. And then actually, let's do this. So I'll start this again, but I'm going to give it an order. Order blah. It doesn't matter, right? Makes no difference. And so order satisfied, so you can get rid of some of these things because you don't need to hit order creator. That's the idea of Argyll at the end of the day. And then, as we're watching this, we're seeing that the flows that we started before, they're completing in the background. And actually, they've all completed. So yeah, that's it. Interesting thing, nothing changed on the front end. In the Docker Compose setup, there is now HA proxy. It's doing the work of making sure that, you're round robining on all your read requests. So like for anything that just hits a projection and there's a query, then it can round robin. It doesn't matter. You can distribute that load. But for all commands like write requests, like create a new flow, create a new step, and so on, it will route those to the leader so that it just makes sure that there's kind of like a hot path for those things to change and avoids the forwarding that the nodes would otherwise do. So big change. It's not a change that you would see, but from sort of an operational point of view, it's actually considerable change. And it's more than likely over the next, I would say, couple of weeks, it will become just the way that Argyll does it. I will probably just remove the Raft experiment branch in the repo altogether and just merge all this stuff into the main and get rid of the Redis backend. I love Redis. I may have become one of the foremost Redis experts over the last months. But for the purposes of this project, I think Raft is probably the better way to go, and it performs good enough for 80% of the kind of use cases that would be hitting this thing. All right, well, so there you have it. That's the update. I think it was kind of long this week. My apologies, but there was a lot to catch up on, and I had realized I hadn't never even looked at code or showed any code, so you got to see a little bit of code as well. So have a good week.